straight line. It's a one-to-one relationship between the independent variable and the dependent variable, x and y. You're also familiar with the form of y equals x squared. It's in the form of a parabola, right? And the way that works is it's a curve. For this equation, it goes through the origin, having a parabolic shape. Today we're going to learn about a different kind of function. It's called an exponential function. So does anyone have any idea what an exponential function behaves like? Have you heard the term exponential increase?
Yes.
Yeah. If you look at bacteria, the way bacteria is cultured, the culture in the bacteria, it grows exponentially. In other words, it multiplies itself at a very fast rate, right?
Yeah.
You've heard about that. Okay, so let me do a comparison between the parabola, which is say y equals x squared, and an exponential function, which I'm introducing now, which says y equals 2 to the power of x. You notice the difference between these two? The variable here is the base, x. In an exponential function, the base is constant, but the variable is the exponent. So how does this function behave? So I'm going to take an example from your notes. Y equals 4 to the power of x. So let's take values of x that are listed here. So what would the value of y be when x is minus 2? Casey, do you know? What's the value of y if x is minus 2 here?
Is it 0.04?
Actually, it'll be 1. If it's 4 to the power of minus 2, that's also stated as, you bring it to the denominator, 4 squared, right? So that's 1 over 16. So the y value is 1 over 16. So what would be the value of y if x is minus 1? If x is minus 1?
1/4.
1/4. Okay, you got it. Similarly, if x is 0, what's any number to the power of 0 is? 1. Right? So that's a 1. 4 to the power of 1 is 4. 4 squared is 16. So if I had to plot this curve, let me plot it on a different piece of paper. If I had to plot this curve, 1, 2, minus 1, minus 2. And if I go up here, if it's minus 2, it's 1/16. So it's a very point right above the x-axis. If it's minus 1, it's a quarter. So it's right here. If it's 0, it's 1. If it's 1, it's 4. And if it's 2, it's 16. So it goes way up in the chart. So an exponential curve looks something like this. Okay? Now let's take for example, remember in the warm-up I gave you a question on if you had $100 in the bank at an interest rate of 5%, what would be the value in your account after 2 years? So how did you solve that problem? Simple mathematics.
I took 5% of 100, which is 5, and then I multiplied it by 2, so I got 10. So I got 1. What? I'm confused now. I got 110.
You got 110, okay.
And 25 cents.
Anyone else have any ideas? Okay, let me show you how you would approach this mathematically. So I have $100 in the bank, and I get 5% interest. So 5% is 5 divided by 100.
So you're going to times 0.05 times 100, you're going to get $5 basically. And since it's 2 years, you're just going to add another 5, so you get 110.
Okay, if it was simple interest, that's true. If
But
it was, okay.
Don't you have to find 5% of what you have over 1 year and then add that to what you made over the first year?
Right. That's compound interest.
So it should be 110 and 25 cents, right?
Okay, let's do it mathematically.
Okay.
So you get, so at the first year, after the end of the first year, you have $105, right? You have 105. So at the beginning of the next year, you have 105, and you add 5% interest to that. So what's 5% of 105?
$5.25.
Okay, so $5.25. Wow. So that's $110.25. Okay? Mathematically, if I had to do this, I would say 1 plus 0.05 at the end of the first year. At the end of the second year, it would be 1 plus 0.05 multiplied by again 1 plus 0.05. You get it? This is at the beginning of the first year. I add 5% interest, so I get 1 plus 0.05. At the beginning of the second year, this is what I have right now. So at the end of the second year, I would multiply that by 1 plus 0.05. And that's equivalent to 100 times 1 plus 0.05 squared. Right? So what would be the interest after 10 years, say? If you use this as a model, what would be how much would you have in the bank after 10 years instead of 2 years?
Would that be to the 10th power?
Right.
Oh, yes.
You replace that 2 with a 10, so that's what you'd have after 10 years. So that's a simple introduction of an exponential function. If you had to plot this curve over time, you'll find that it would have a curve like this, an exponential function. Okay? Now there are a few characteristics in your notes. If you look at your notes, there are a few properties of exponential functions which you need to be aware of. So you notice this curve doesn't have a break anywhere. It's continuous. Right? Unlike those rational functions where we looked at where there's potential for holes and asymptotes, an exponential function is continuous. Right? And it's over the range of all real numbers. If you look at x as an axis, these are all real numbers. And the graph, the way, if you look at the graph, the way I had plotted it here, this is an asymptote. The x-axis is an asymptote to this graph, isn't it? This line never reaches negative infinity, never reaches that point. It's always close to it, but never reaches it. So this is an asymptote. Okay. Okay, so that's one example that I mentioned about an exponential function where the value of the base, in this case 2, is a number greater than 1. Okay, so let's let's do another graph where the base is less than 1. So let's take a half, for example. Okay. So I'm going to plot a graph y equals half to the power of x. So I take the same values, x and y, minus 2, minus 1, 0, 1, and 2. So if x is minus 2, let's replace x with minus 2. What would that be? What would half to the power of minus 2? Can anyone, Kyle, do you know? How would you do this? The first step, take the reciprocal of the negative exponent to make it positive.
So it'll become 2 to the power of 2?
No, it'll be, you bring this whole expression down in the denominator, right? To make the exponent positive, right? So what's that equal to? This is 1 over 4, right?
Yes.
So that becomes
4.
4, right? So if x is minus 2, y is 4. Let's take x of minus 1. What would that be? Aaron, what would that be? Half to the power of minus 1.
Isn't that just negative 1/2?
Follow the example we did up here. So you want to make the exponent a positive number, right? It'll be 2, right? The way you do it is you change the sign of the exponent by going into the denominator, right? And that's 1 over a half, which is 2. So if x is 0, half to the power of 0 is
Always 1.
always 1, right? If x is 1, it's a half. If x is 2, it's a quarter. So if I had to draw this curve, x minus 2, it's 4, say here. Minus 1, it's 2. 0, it's 1. 1, it's a half. And this is a quarter. So you notice the curve goes from left to right. The other curve we did for a value greater than 1, the curve went something like this. So this is the base greater than 1. This is the base less than 1. Less than, between 0 and 1. So in the way you express these both these curves is, this is an exponential growth, this curve, and this is an exponential decay. Okay? Two new terms. Exponential growth is growing, exponential decay. The decay, if you spend too much money from having a fun time, your bank account takes an exponential decay. If you earn money, you have a growth of this value. So that is pretty much the terminology that I want to introduce to you. So let's do some work on the next page. Can you work on example 3? I'll just come around and see how it's going.